Okay, so finally we come to the more interesting part. So in this module, we'll look at gradient descent with adaptive learning rate. So first we'll see motivation or intuition for why we need this. And once we get the motivation, I believe the rest should be straightforward. Okay. So far what we have been doing is, so please pay attention on this slide. I need to define some notations and you shouldn't get confused with them. Okay. So far we have been dealing with a situation where we had just one feature, which was X, and one weight corresponding to it, which was W, and one bias which corresponded to the always on input, right? Now we are going to look at a situation where we have more than one inputs. That means earlier we were basing our predictions only based on the director. Now we have the director, actor, genre, IMDb ratings, and so on, right? So here X1, X2, X3, X4, these are four different features or four different inputs that I have, okay? And these are not, this is not X squared, just, I know it's obvious, but I'm just making it clear, right? So this is X1, X2, X3, X4, okay? Not probably the best choice of notation, but I'll just stick to that. So now each of these has a corresponding W1, W2, W3, W4, okay? And this is how your decision looks like. It's the dot product between the weight vector and the input vector, okay? This is how I'm going to decide, and that's a single sigmoid neuron again. Now, so given a single point x, y, do I need to again go through this computation? Sorry, W comma P. Oh, sorry. Okay, I'll just erase this. So this W is actually the vector W, so it includes W1, W2, W3, W4. And I am trying to take the derivative with one element of that vector. Do I need to show you how to compute this? Have you seen this before? Okay. Can you tell me, I will show you the derivative with respect to W1. Can you tell me, it will be a product of some terms. Can you tell me what is the last term going to be? Everyone gets this? You remember this from, so only thing which is changing is this guy, right? So this part is exactly what we had derived. And when we had one input, we are just calling it X. Now we have multiple inputs. So it will depend on that particular input, right? Whichever W1 corresponds to. Okay. Now make an interesting observation there. Okay, so, okay, sorry, before that, yeah, this is obvious. If there are endpoints, we'll just take the sum of the gradients with respect to the endpoints. Okay. Now, what happens if the feature X2 is sparse? What do I mean by that? It's mostly zero. Okay, what does that mean? So I'm looking at a lot of movie data. Okay, Aamir Khan acts in a very few movies. So if I have a feature which says is actor Aamir Khan, then that's going to be zero for most of the movies in my data set. Right? That's what I mean by sparse. Okay, so if I have 10,000 movies, then probably only 50 of them would have this feature as on. Okay, does that make sense? So it's going to be very sparse. Now, if the feature is sparse, why do we care about it? What will happen? What do we really care about when we are talking about optimization in this course? The gradients, right? That decides how well we move in the plane that we are considering, WB plane or the other, in the n-dimensional region that we care about, okay? So now, if X2 is sparse, what would happen to this? It will be zero a lot of times because X2 is zero a lot of times, right? So now just take a minute to understand this, right? So now remember, let's talk about stochastic gradient descent or mini batch gradient descent or even batch gradient descent. You're going over all the 10,000 points that you have. You're computing the gradient with respect to all the parameters. One of those parameters happens to be W2, right? You have gone over 10,000 points, but in how many of those you will actually get the gradient for this? Only in the 50 in which X2 was present, right? Everywhere else the gradient would be zero. So that means your sum of the gradients over all the n points is going to be small or big? Small. For this particular feature or for this particular weight, it's going to be small, right? Because you don't have enough samples where you are seeing this. So now, what would happen to the update? You started at a random value for W2, okay? After one epoch or making one entire pass of the data, what would happen to the updates for W2? very small, very few updates. Compare this to a feature which is dense. It will get a lot of updates. So you see there is something unfair happening here. If a feature is sparse, it's not getting updated enough, right? Now that was okay in one situation if this feature was not really important, okay? But now consider the exact example which I gave you, which is this an Amir Khan movie or not? Now suppose I'm doing a classification whether this movie is going to be a hit or not. I would believe this feature is very important because almost always when he is the actor, the movie is a hit, right? So you really can't ignore this feature. You want to learn the parameters correctly for this feature. Do you get the setup, right? There could be cases where your feature is very sparse, but at the same time very predictive of the output that you're trying to learn, right? And in this case, the output is whether the movie would be a hit or not, okay? The other example could be is Christopher Nolan the director, so he has probably directed less than 10 movies, but all of them have been at some point in the IMDb top 250 or something, right? So that's a very important feature, but you will not get it very frequently in your data, right? So you can't really ignore these features. That means you still want to learn these features properly. So you have sparse features, you have dense features. We understand that for the sparse features, the updates would be slower. For the dense features, the update would be faster. Okay, all of us get this? Fine. No, the sparse would be 0 in most cases. No, so you will do this 0 mean thing, right?
Yeah, but I'm saying that.
No, but if it's the same value and you're going to 0 mean the data, right? So the value, even if it's 1, it is going to be very close to 0, right? So you always assume 0 means, otherwise all this does not make sense, right? Because if your features are not in the same range, then anyways you're in trouble, right? Okay, fine. So this is what I was trying to say, that the gradient with respect to WT is going to be 0 for most inputs, and hence WT will not get enough updates. And as I said, if this is an important feature, we can't really ignore it. We have to make sure that it learns better. So what is the case that I'm making for? What do we actually need? Can you relate it to the discussion on learning rate that we have been having? So if the feature is sparse, you know it's going to get very fewer updates. So can we change its learning rate so that that feature gets updated a bit faster as compared to the other features? So you get the motivation, right? How to do this is a separate story, but at least we need to do this. Is that clear? How many of you get this? Okay. Fine. So the intuition is decay the learning rate for parameters in proportion to their update history. So you have been recording the update history. You have been looking at a parameter. You know all the gradient W2 that you had calculated so far, right? How many times you had computed the gradients and what those values were actually. Now for the sparse features, those are going to be 0. So your accumulated history is going to be small, right? For a dense feature, it's going to be high. So why not make the learning rate inversely proportional to this history? That means if the feature has been updated fewer times, give it a larger learning rate. If it's not updated, if it's updated many times, give it a smaller learning rate. Can you give me a mathematical formula for doing this? This is the intuition. Just think about it for a minute. Learning rate inversely proportional to update history. Okay? Okay, good. How many of you get that? But most of you will get it once I show you the answer. This is my gradient which I had computed so far. I mean at this time step. I'll keep accumulating it in a history vector. Okay? So at time step 0, I'll take the magnitude of this. Again, I'm taking the magnitude, right? Because it doesn't matter whether you made an update in the positive direction or the negative direction. It just matters that whether how much by how much did you move. So I'll just square this quantity so that I can get rid of the sign. Okay? So I'm taking the magnitudes and I'm storing all that. So at time step t, what would Vt contain? Grad W0 square plus W1 square, grad W1 square and so on up till time step t. Okay? Now, this was my, if I ignore this quantity, this was my normal gradient descent update rule. Okay? Now, do you see what I have done? I have divided the learning rate by whatever history I had accumulated. So for the dense features, what would happen? The learning rate will increase or decrease. With time, the learning rate will decrease, right? And for the sparse features, relatively less, right? And in fact, if you have gotten 0 updates so far, so when you are updating it the first few times, you'll have a very high learning rate. Does that make sense? Right? Because this quantity would be 0, so your eta would actually be very large. Okay? So you see how that intuition got converted into some reasonable formula. Okay? Fine. And now Can you tell me a way of actually realizing this? I want to show you that what happens when you have sparse data. And I want to do this with the toy example that we had, where we had only one feature and the other feature was always on, right? So how do I create this sparse data? So you should think about these, because these are things you'll have to do when you're practicing machine learning, right? So if you're working with the problem and you want to create some simulated data so that you can verify some hypothesis that you have. So how would you do this? Say I'm going to create 1000 data points, right? Which is x comma y points. And of course I have this x0 which is always on, right? So x0 is always on, I can't make that sparse. What about the other feature? If I'm creating 1000 data points, what should I ensure? That 80% of them or some 90% of them is always 0, right? Just as the Aamir Khan case, right? That most of the data is going to be 0. So what we'll do is, as I said, we just have two parameters w and b. B we cannot make sparse, it's always going to be on. So what we'll do is, we'll make x sparse. We just create random x comma y pairs, and then for 80% of those, we'll set x to 0, right? So now this x feature is going to be very sparse. Is that fine? So now I have created some data which is sparse, one of the features is sparse, and now I want to see what happens when I run gradient descent, momentum, and Nesterov accelerated gradient descent, and how does the algorithm behave. And now if I apply this algorithm, which I did not name, it's called AdaGrad. Okay, this algorithm is called AdaGrad. If I apply this algorithm, then how does the situation change? Okay, fine. So this is what gradient descent, momentum, and nag do. Now at least the difference between momentum and nag should be clear. The nag blue curve is inside the red curve, right? So the oscillations are slightly smaller. Okay, this is how they behave. Okay. Now there is something very interesting that these three algorithms are doing for this particular data set that I have created. Can you spot it? What is the interesting thing happening here? I want you to take some time and think about it. And relate it to the discussion that we just had. How many of you see what is happening here? Okay, very few. I'll give you a hint. Okay. It's almost as if these algorithms went to a school where they did not teach Pythagoras theorem. Now relate it to the discussion that we just had. What is happening initially? So initially what is happening is, you started from here, okay? And this is the w comma b plane. So you have w on the horizontal axis and b on the vertical axis. What is happening to all your updates initially? Where are you moving? You are moving along the b direction. Are you making any movements along the w direction? No. Why? W was sparse, its gradients are mostly 0. It was not being able to make any updates in the w direction. All it was able to do, make updates in the b direction. It did as much as it could do. After reaching here, it realizes that there is no point in going to b further, right? It actually took a U-turn because it realized that there's nothing, I can't really go ahead. I have to now start walking in the direction of w. So now in practice, although in this toy example it still converges fast, but in practice what will happen is, you have just moved in one direction, reached a point, and now from there again you are going to take a right turn and reach to your destination, right? So you're doing something which is not faster. This is not how you would go from this point to this point. There has to be a better way, right? And this is happening because W is not getting updated frequently. All the updates are initially done for B, and now when it's no longer possible to change B because you have reached the optimum value for B, then only you start changing W, and that too very slowly because you'll have to wait for many updates for that to happen. How many of you get this? So this is exactly what's written on the slides. Because in our data, the feature corresponding to W is sparse, and hence W undergoes very few updates. And B is very dense, and it undergoes a lot of updates. Okay. Now, such sparsity is very common in large neural networks, which have thousands of features, right? So you could imagine this. Now, if I have thousands of features, now suppose I am doing credit card fraud detection. Okay. Now, say one of my features is corresponding to some education that the person had, and suppose he has done some very less sought after degree or less sought after curriculum, right? So that feature is going to be sparse for most of the cases, but I can't ignore it. Maybe this is the most predictive feature that I might have, right? So you could think of various cases where you would have thousands of features, out of which many are going to be off for a given example, right? Everyone sees that this is a real world scenario where a lot of your features are going to be sparse, and in many cases you cannot ignore the sparse features. Okay, fine. Now let's see what AdaGrad does. Any guesses? Okay, good. So I'm running this. You should start seeing something, a green curve starting from here. Okay. Do you see what is happening? Expected. Now try to guess if you are going to run into a problem. I have deliberately halted the algorithm. I just want you to think if you are going to run into a problem. Okay, all of you are thinking of something which makes sense. So now I've run it for, in this case, again this is a toy example, hence you don't see a lot of difference between these algorithms in terms of number of steps taken to converge. But in a real world application it would be very different. But now what has happened is, I've run the algorithm for as much as I can and I've been stuck here. I'm not being able to move forward. Why is this happening? Well, the history is accumulating, it's growing. Now what am I doing to the learning rate? I'm just killing it, right? It's eta by a very large constant now, and that's going to be very, very, very small. So no matter how big my gradient is, it's going to get multiplied by a very small learning rate, and I can't just move any forward anymore, right? So you see that will happen. That's why this, in this case, okay, this is some point here, which I don't want to go over now, and it's this, in fact I don't have an explanation for that, but this one observation which people have made, that remember we had the square root in the denominator. If you remove the square root, in principle you are still doing the same thing, right? You are still making it inversely proportional to the accumulated history, but it doesn't work well when you do that, right? So I don't know why it happens, and I've just read these comments at several places that it does not work when you remove the square root from the denominator, but that's not important for this discussion, that's just a point for reference later on, okay? So right now what I'm trying to say is that it did the right thing. It started making updates for W also and started making larger updates. Hence we see this simultaneous movement in both W and B direction. But the flip side is, over a period of time, the effective learning rate for B will decrease so much that we will no longer be able to move in the vertical direction, right? And if you're not being able to move in the vertical direction, will not reach the minima in this particular example. Not always, but in this particular example, you need to move further in the direction of B, but your learning rate is not allowing you to do that, right? So that is what is happening. So now can we avoid this? Yes. How? Multiply by? So first divide it so that it decreases, then multiply it so that it does not decrease. All of these are interesting ideas. It's very hard for me to say upfront whether this is wrong or right. But yeah, these are, you get the idea basically. Something is happening which is, you are aggressively killing the learning rate. Now we just want to make sure that we are not so aggressive, okay? So what happens because of the aggressive killing is the frequent parameters, they start receiving fewer updates. Now this is what RMS prop does, okay? I want you to stare at this for a minute, okay? Assume that beta is going to be something which is greater than 0.90 or 0.95 or something, and try to make sense of what is happening. Try to imagine what is VT going to look like, okay, in terms of grad W0, grad W1 and so on. So start from V1 and see what happens. What was V1 earlier and what it is going to be now? Okay, but that still grows my magnitude, right? I'm still adding stuff. So how does it help me in not blowing up the denominator? Okay. So yeah, I think most of you get it. So again, this is the trick, is basically you're using this exponential moving average, right? So even at the first step, earlier I was doing grad WT square. Now I'm actually doing 0.05 into grad WT square. Oh sorry, grad W1 square, right? So that's what my V1 is going to be. Now what is my V2 going to be? It's going to be 0.95 into 0.05 grad W1 square plus grad W2 square, right? So this quantity is even shrinking further. And at each step, this is going to keep a 0.05. Okay? And you see now that at each step, this is going to get multiplied by this quantity and shrink further. Okay? So now I'm not aggressively growing the denominator. I'm not considering the full gradient, but only a fraction of it, and in fact, a very small multiple of it. So I'm still accumulating the history, but I'm not being very aggressive while doing that. Right? So you understand this? Everyone gets this? Okay. So now let's see if we run, what would happen. Any guesses? Okay. So initially now, this is I think a brown curve. It's already there, but you can't see it. So I'll keep running it. At some point it will diverge from the green curve. Yeah. Do you see that now? has reached its destination, right? So at the point where the B learning rate, the learning rate for B was getting killed, in this case that does not happen because you have prevented the denominator from growing very large. You have actually multiplied by its small values so that it does not grow very fast. How many of you get this? Okay. Not as many as I would like. Can you please raise your hands? Okay, there are some people are just lazy. Fine. So ADA got stuck when it was close to convergence because the learning rate was killed and it was no longer able to move in the direction of B. But for RMS prop, it overcomes this problem by not growing the denominator very aggressively. Okay. Now, can you think of any further modifications to this based on everything that you have learned so far? And by everything, yeah, so I'm not very sure why that. I agree that I am also a bit surprised that it completely overlaps with it. I've checked it and that's how it turns out to be. I'm guessing it's an artifact of the artificial data that I've created. So what he's trying to say is actually making sense that it should not overlap so much, right? Initially, it should slightly be biased towards B and then probably, that's what you're trying to say, right? But I don't know, it's just an artifact of this data that I have. But what matters is from the, I was going to say illusion, but from the illustration, is that it actually does not kill the learning rate, okay? Fine. Okay. Yeah. So what is the one idea that, now think of everything that you learned in starting from gradient descent, then you tried to improve it using something, then you tried to further improve it and so on. And now you have taken a slight detour from there, you're now focusing on the learning rates, but there were other things which you were doing earlier. Can you bring those back? Add momentum. How many of you say add momentum? As if it's just, I can just add it. No, you're right actually. Okay, so let's see what we can do. So it does everything that RMS prop does. That means it tries to make the learning rate inversely proportional to a sane accumulated history. By sane I mean it does not allow the history to blow up, and it also uses the cumulative history of the gradients. So let's see the update rule for Adam. So what is this term doing actually? It's taking a moving average of the, this is the same as the momentum based rule, right? This is taking a moving average of your gradients, okay? The same analogy that I'm going to Phoenix Market City, I'm just taking all my history into account, okay? And VT is again a cumulative history. This is the same as what was happening in RMS prop, right? Why are you guys lost? Is this fine? Everyone is okay with this? Okay. Now what would the next step be? Can you give me the final update rule? At least think about it. MT into VT, no? Okay, just try to think about it. Right? It's very hard to say it out. There are too many grads and suffixes and so on. So just think about what you did in the momentum case. Okay. So now there's one more step which I'm going to ignore. I'll just say what that step is and then I'll come back to that later on. So this is something known as bias correction. Okay. Just ignore it for the time being. I'll come back to this discussion. Just for the time being, just assume that I'm taking MT and dividing it by some quantity, right? So for all practical purposes, I'm just using MT, just dividing it by a quantity. Okay, just for now, that should suffice. And then my final update rule is going to be this. How many of you expected it to be this, or at least understand that this is fine? Not many. Okay, so let me go over this. What did you expect here? In the normal gradient descent, this should have been grad WT. That means the derivative with respect to current W. Okay. Instead of that, I'm using the accumulated history. Instead of using just this quantity, I'm using the accumulated history. Does it make sense? This is the same as momentum based gradient descent. How many of you get that? Okay. And now this quantity, there's nothing new. This is the same as what RMS prop suggested, that you divide the learning rate by the accumulated history of gradients, right? So it's just a combination of these two. One is take care of the learning rate, the other is use a cumulative history. Does it make sense now? Okay, fine. Now this part is something that I need to tell you about. So I'll tell it to you after I run the algorithm, and then I'll come back to that. But is the update rule clear that it's a combination of momentum plus killing the learning rate? Okay, fine. And a similar set of equations for BT. Now let's see what happens to this algorithm is actually called ADAM. It stands for adaptive moments, right? Yeah. What is? Can you tell me why that name? Huh? Why moments? Good. Where is the mean here? Is this a mean? This is a moving exponentially weighted average, right? This is exponentially weighted mean. What about this? What is this quantity if you take the average of this? This is the second moment, right? Exponentially weighted second moment, right? So using the first moment and the second moment to come up with an adaptive learning rate. Okay? Is that fine? Okay. So now I'll run this algorithm. Are you able to see the cyan colored curve? Okay. So it's here. You see that now? Okay. Do you see what happened? Do you see this curve? Everyone sees that? Okay. So what is happening? It's taking U-turns, right? So again, whatever happens because of momentum is happening in this case also. And then finally it will converge. Again, let me be clear that in this, now it should be very clear. We need to change, who is the TA for this slide? So this color needs to be changed, or it should be bright right from the first. So what is happening is it's getting overlaid and then it becomes bright, but we need to have a brighter color right from the beginning. Okay. So yeah, so this again in this toy example, right, you don't really see the speed as such because all of them are converging in almost the same number of steps, but this again I repeat for the toy example, but at least you see that the behavior is very different. And behavior is consistent with whatever you have put into the update rule, right? In one case, the learning rate gets killed. In the second case, it does not decay. And in the third case, when you're using this this momentum term, you again have this behavior similar to the momentum gradient descent where you actually overshoot and then you come back, okay? So is that clear, all these algorithms? Okay. Now, here's the $1 million question, right? Which of these do you use in practice? So what are the options that you have for your backpropagation assignment? Even if you have not read the assignment, you should just tell me based on whatever you have learned. You have gradient descent, momentum, NAG, RMS prop, ADAGRAD, ADAM. Okay, so which of these would you choose? And in fact, there is one now which is called EVE. Okay. But it did not really gain much momentum. But ADAM, okay. So in practice, ADAM seems to be more or less the default choice. I should tell you that recently there was a paper or a couple of papers which actually show that there is a slight error. You could show cases where ADAM will not actually converge as expected, right? But still then after that, as is the case in whole of deep learning research, is that one person says this works and immediately the next day someone else says this does not work, or vice versa, right? So someone showed that this does not work, ADAM does not work in some cases, but then someone else did a detailed study showing that in most practical applications, okay, you have taken a toy data set where you can show some things under some conditions, ADAM will not converge. But if I look at real world data sets like MNIST or ImageNet or something, those conditions don't hold there, and so ADAM really works with. So in practice, ADAM is more or less the standard choice nowadays, at least all the image classification work which deals with convolutional neural networks and so on, that uses ADAM as the optimization algorithm. We have used it largely for a lot of sequence to sequence learning problems, and it works well. Although it is supposed to be robust to the initial learning rate, right? Because you are tampering with the learning rate as you go along, right? You're not sticking to eta, but you're conveniently blowing it up or shrinking it based on your requirement. So it should not be sensitive to the initial learning rate. But we have observed that at least for the sequence generation problems, If you use one of these learning rates as the starting point, they work best. Of course, these are again heuristics, right? Because it also depends on how much data you have and so on. If you're going to train with only 1,000 samples, then first of all, of course, you should question why are you using deep learning. But if you have gone past that question already, as everyone else has, then you might still be using a deep neural network. And in that case, maybe these learning rates are going to be very small. But in general, for a large number of data sets out there on which a lot of academic research happens, which are of a reasonable size, these learning rates happen to work well in practice. Okay. Now, having said that, many papers report that SGD with momentum, either the Nesterov momentum or the vanilla momentum, with a simple annealing learning rate, right? We remember we did this learning rate decay, either a constant decay or that heuristic decay that after you look at the validation loss and then decide whether to decay or not. That also seems to work at par with ADAM, right? So my advice would be that if you really know what you're doing with SGD and momentum, right? That means if you really know how to look at the loss, how to track it, how to adjust the learning rates and so on, with a little bit of manual tampering, it should work as well as ADAM. There are papers which show that it works well as ADAM. But if you're just a practitioner who doesn't really want to bother too much about setting the learning rate, setting the momentum, setting the schedule for both of them. Remember, for momentum also we had a schedule and it was just given by one of these papers, right? And it might differ for your application. You might want to tweak that a bit. So if you're not really bothered about doing all these things, then ADAM would just be overall the best choice, right? With very minimum tempering of the initial learning rate, right? And as I said, some recent work suggested there is a problem with ADAM and it will not converge in some cases. But then that's, it's still, I would say the jury is not out on that yet. Because there is this, of course, theoretical angle to it and also the practical angle to it. In practice, it has been used widely for the last 3 to 4 years at least, and it works well in a large number of applications, right? So that's why ADAM would typically be the overall best choice, okay? Now there's this one thing which I need to do, which is I need to tell you why do we use this bias correction. So now what do you actually want to do? You're taking a mean, okay? You don't want to rely on the current estimate of the gradient, but you want to take a exponentially moving average of the gradients, right? Now what would you actually, why are you doing all this? What's the intuition behind this? Since you're talking about moments and so on, can you think in terms of probability distributions? So, okay, let me just try to say it this way, right? That your gradients, your values of grad WT, right? And I'll just, I think, alternately use GT instead of grad WT. It just means the gradient at that point. It actually comes from some distribution. Depending on the point at which you are, right, the gradient would change, but it comes from a certain distribution. And now what do you actually want at any time step when you are making this update, this particular update, okay? Is it clear? Yeah. When you're making this update, what would you actually want? It should not move too much away from the, sorry. So now your gradients, how are you computing? Say if you're doing the stochastic version. You're computing it for every point that you have, right? With respect to that point, you would have some loss function and some derivative with respect to your parameters. If you move on to a different point, you'll have some different parameters. So there's some randomness in this, okay? So I'm saying that these gradients could be treated as random variables, which can take on values according to a certain distribution, okay? And now what do I mean that, so what would I actually want when I'm making an update? So I have to, the basic choices I could have just used grad WT, right, which is the derivative with respect to the current time step, at the current time step, okay? Instead of that, I know, why am I not happy with that? Because it has this problem that it could pull me to the extremes, right? That this point is actually saying, okay, it changed your W value in a particular way, which is most suited to me. Some other point would say something else. So what we want is that whatever update we make should be very close to the dash of the distribution, mean of the distribution, right? And instead of computing the mean, we are computing a moving average, an exponentially moving average, okay? So now what do we actually want? Say I said that GT is the random variable for the for denoting the gradient, okay? What do I actually want? I want the expected value of MT should be equal to what? the true expected value of GT. This is what I want, because I don't want my updates to move in the extremes. It should be closer to the average, to the mean of the distribution. Do you agree that this is my wish list? This is something that I should desire for. Okay. Now let's see, what is MT actually, if I want to write it as a formula. So I have MT is equal to 1 minus beta, no, I'll call this as GT, right? So remember that GT is grad of WT. Okay. So now let's try to write a formula for this. So M0, I'll set it to 0. So M1 is going to be 1 minus beta into G1. Okay. M2 is going to be beta into 1 minus beta into G1 plus 1 minus beta into G2, and M3 is going to be beta into 1 minus beta square G1 plus beta into 1 minus beta square minus beta. Wait, is the first term correct? No. Beta? Okay, so wait, what am I, oh, beta is getting multiplied, okay. To G2 plus 1 minus beta into G3. So what is the general formula going to be? MT is equal to, so 1 minus beta can come out, okay. Summation I is equal to 1 to T 1 minus beta, oh god, sorry. Beta raised to T minus I and Gi, right? Okay. So this is what my MT is. Okay. Now let me take the expectation of this. Okay. This is fine. Now, okay, this should be 1 minus beta. So now this is going to be is that fine? Okay. Okay, okay. So what is this? It's an AP, GP, GP. What's the sum going to be? It's going to be 1 over 1 minus, no, it's actually, no, sorry, 1 minus beta raised to T over 1 minus beta. Is that fine? Okay. So what will happen? This will get cancelled, and what you are left with is 1 minus beta raised to T into E of GT. Okay. So what is the relation that you have? E of MT okay. E of MT is equal to 1 minus beta raised to T into E of GT. What did you actually want? Right. So now how will you ensure that? Divide MT by 1 minus beta raised to T, and that's exactly the bias correction that we had done. Okay. Sorry about this messy derivation, but I guess most of you get it. If not, we'll just type it properly and upload it in the slides. How many of you got this? Okay, most of you got it. Fine. So that's, and the similar derivation for VT also. Okay, fine. So that's why we need the bias correction.